Hi folks, welcome to Blended Learning Day. We are going to do a teeny tiny unit on probability. So we're going to start with a short video. You're going to complete your guided notes. Your teachers should have given you guided notes. We will have a link to that on Blackboard. So if you need to go print those out because you forgot to bring them home, you can do that. And then after you finish watching this short video, you'll go take a Blackboard quiz and I'll talk more about how that's being scored later. So our goals today are to solve problems using the fundamental counting principle. We're going to find theoretical probability of an event. We're going to determine whether events are independent or dependent. And we're going to find the probability of dependent events. Okay, so the very first thing that we need to do is go over some definitions. Rather than have you guys get writer's cramp, I've already provided all the definitions for you on your guided notes. So the definition of probability is it's the measure of how likely an event is to occur. Probability is written as a decimal or a fraction that goes from 0 to 1, or as percentages that go from 0 to 100. So the probability of rain could be 60%, that kind of thing. A sample space is the list of all possible outcomes, and we do that in set notation. So when we talk about rolling a die, for example, the sample space is in brackets, and the sample space is 1, 2, 3, 4, 5, 6. An event is an outcome or set of outcomes. So we could talk about the probability of rolling a 3, and that would be an event. And then the outcome is the possible result of a situation. So that's our basic vocabulary. There's going to be more that we add. But first, let's practice writing a sample space. So Halloween is coming, and I've got this bag of Mars chocolate favorites that I got off the internet. And this bag has 60 pieces of candy that is Milky Way, Three Musketeers, Twix, and Snickers. So how would you write that in set notation as your sample space? Well, this is what that's going to look like. Just in the bracket notation, you're going to write the different candies that are possible outcomes, things that you could pull from that bag. Milky Way, Twix, Three Musketeers, and Snickers. Those are the only possible things to pull from that bag. That is the complete sample space. All right, the next thing that we need to talk about is the fundamental counting principle. And the fundamental counting principle states that if one event has m possible outcomes and a second independent event has n possible outcomes, then there are m times n total possible outcomes for the two events together. So let's say you go to Subway and you're going to get a sandwich and a drink. Well, I've never actually counted the amount of items that are at Subway in terms of sandwiches, but let's say that there are 11 different kinds of subs that you can get. Now, we're not going to talk about all the different vegetables that you can get on there and how you can customize it. Let's just talk only about the Philly cheesesteak or the veggie and cheese, the turkey, the Italian, whatever, those basic sandwiches. So let's say they have 11 sandwiches to choose from. And then you're going to buy one drink. And when you go over to the soda fountain, there are, what do you think, maybe 8 kinds of soda that you can choose from. So that means when you go into Subway, you have 11 sandwich options times 8 soda options. So you could walk out with 88 possible combinations of a sandwich and a soda. So this is what the fundamental counting principle means. If you've got one event that has m items and the other event that has n items, the possible outcomes is m times n. So let's talk about this in another example. You're getting dressed, and let's talk about this in terms of you want an outfit that looks different for a number of days. So we're not going to talk about things that don't get seen. So we don't have to talk about undergarments per se. So when you get dressed, in thinking about this outfit that's going to be seen by others, we're looking at shirts, pants, socks, and shoes. And in your closet, you have 12 shirts, 8 pairs of pants, 12 socks, and 5 shoes. So how many possible outfits could you make with that number of items in your closet? Well, the fundamental accounting principle says that if you have, well, let's go look. What does it say? If you have one event that has n possible outcomes and a second independent event that has n possible outcomes, we multiply those together. Well, we sort of have that plus more. So I'm going to say I have 12 shirts, I have 8 pants, I have 12 socks, and I have 5 shoes. So I'm just going to multiply those numbers together. 12 times 8 times 12 times 5, and this is going to tell me the total number of outfits that I could possibly come up with. Let's just for good measure pretend that everything matches everything else. All right, so 12 times 8 times 12 times 5 gives us 5,760. 5,760. So I don't want you telling your mother you have nothing to wear, because you have a lot of outfits that you could come up with. All right, so that's that one. Now, the next thing that we're going to talk about is independent and dependent events. Events are independent when the occurrence of one event does not affect the probability of the other event. So you roll a die and then you flip a coin. So those would be independent events. Those two things do not affect one another. Whereas a dependent event is where the occurrence of one does affect the probability of the other event. So let's talk about your sock drawer. Maybe you have 20 black socks and you have 30 blue socks. You have a lot of blue socks, you know, NDCL and everything. So in your drawer, you have a total of 50 socks, right? So you go to your drawer and you pull out a black sock. You pull out one black sock and you go to pull out, black has an L in it. You go to pull out a second sock, but now in the drawer there are no longer 50 socks because one of them is on your left foot. So you go to pull out a second one, there are no longer 50 socks, there are 49 socks. So that's what it means when one affects the other. Something changes. So in this case, our number of events changes from 50 to 49. That's what a dependent event is. Now today, we're talking mostly about independent events. So let's talk about this example. There are 5 drivers at your house. Your grandmother lives with you, you got an older brother, an older sister, mom and dad, everybody has cars. So how many different ways can we possibly get 5 cars parked in this driveway? So in this first slot, how many different cars could park right here? Well, this red car could park there. This blue car could park there. This pink car could park there. This yellow car could park there, or this green car could park there, right? So there are 5 different choices. Well, let's put the green car there. He's in the first spot. So how many cars can fit? There were 5 choices in this one. How many cars can fit in this second one? Well, now the red guy, the blue guy, the pink guy, and the yellow guy, they're all available for this. Let's say the pink car comes in here. So there were only 4 choices for that block, right? Well, how many choices do we have for this third block? Well, now there's only 3 possible cars that can go in this position, right? The red car, the blue car, and the yellow car, they're the only cars left. So we'll just arbitrarily put this red car down there. There were 3 options for this block. How many options are in this block? Well, now there are only 2 cars left. And then this last spot, there's only 1 choice there. So let's put him there. There's only 1 choice. I could take this out and rearrange these cars and we could figure out how many different ways we can do this. Or we could know that this is the fundamental counting principle. So this is 5 times 4 times 3 times 2 times 1. Well, 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120, and 120 times 1 is 120. So there are 120 possible ways to arrange 5 cars in this driveway. Well, just so that we know this, you need to see this somewhere. We call this factorial. There are 5 factorial. The exclamation point is the mathematical notation for factorial. And what this means is 5 times 4 times 3 times 2 times 1. What if we had 7 factorial? Well, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So no matter where we start with our factorial, we just multiply all the numbers that go down from that. So if you had 8, it would be 8 times 7 times 6 and so on. So that's how that gets done. So right now there are 120 possible ways to rearrange those 5 cars in the driveway. All right, the last big thing that we're going to talk about is theoretical probability. This is the ratio of number of favorable outcomes to the total number of outcomes. And this is when outcomes are equally likely. So a regular die, a fair coin, a deck of cards. Whereas, you know, if you were having a drawing and you put names in a hat, they're not necessarily all fair because one wad of paper could be bigger or made out of a different kind of cardstock. So not all events are going to be fair, but we're going to assume that everything is equally likely. So our example for this is the probability of rolling a prime number on a fair die. Well, let's talk about what prime numbers are. Prime numbers are numbers that are only divisible by themselves and the number 1. By definition, 1 is considered a prime number. 2 is only divisible by itself and the number 1. 3 and 5, those are the 5 prime, or the prime numbers less than 6, because of course a die only goes up to 6. So 4 is divisible by 2 and 1 and 4, so it's not prime. 6 is divisible by 1, 2, 3, and 6, so it's not prime because it's just divisible by too many things. So we have 4 favorable outcomes. So the number of favorable outcomes is 4, and my sample space is 6. There are 6 items, 1, 2, 3, 4, 5, 6 items in my sample space. So the probability of rolling a prime is going to be 4 over 6. And of course, we're always going to reduce our fractions. I notice that 4 and 6 are both even numbers, so I take a moment to reduce that down to 2 over 3. So the likelihood, the probability of rolling a prime number is 2 over 3. All right, this is it. We're going to talk a little bit about how to deal with the quiz, but for right now, we need to do a couple more examples. So a quarter, a nickel, and a penny are flipped. What's the probability that the quarter shows a head? Well, our favorable outcome is a head, and our total outcomes is head or tails. So we have one favorable outcome over 2 possibilities. And the question throws you off because it talks about a nickel and a penny, but we don't actually care about the nickel and the penny. We're only worried about the probability that the quarter shows a head. So in this particular case, 1/2 is going to be our probability. The next example says, given the days of the week, what's the probability of choosing one that starts with a T? Well, let's talk about our sample space, our total outcomes. There are 7 days in the week, right? And in our fraction, we want to talk about our favorable outcomes being on top. In this case, we're talking about days that start with a T. Well, that's Tuesday and Thursday. So 2, Tuesday and Thursday are our favorable outcomes. So my final answer is going to be 2/7. I can't reduce that. So my probability of choosing a day that starts with a T is 2/7. What if a question was, how many days have an S in it? Well, our total outcomes is still going to be 7 days, but now we have to think a little bit harder. So there's a U in Sunday, so that's one. There's not one in Monday. There's one in Tuesday, so that's another one. Wednesday, nope. Yep, Thursday's got it. Friday, Saturday has one, and that's the whole week. So there are 4 out of 7 days that have a U in them. So the probability of choosing a day with a U in it is 4 out of 7. All right, our last example is you have a bag with 5 lemons and 3 limes. What's the probability of pulling out a lemon? So we want favorable outcome over total outcomes. Well, a favorable in this case is lemon. So we have 5 lemons. Our favorable outcome is 5, and our total outcome, well, we have 5 lemons and 3 limes, so our total outcomes is 8. So the probability of pulling a lime out of the bag, or excuse me, pulling a lemon out of the bag is going to be 5 out of 8. And you can turn around and plug that into a calculator and give yourself a percentage option. So from here, you're going to go over to Blackboard. You're going to take the quiz. You will have 3 attempts. We're going to average the 3 attempts when you're finished, and the average score is going to go into Plus Portals as a 10-point achievement grade. Now, think about what that means. Don't go over to Blackboard and just start hitting A, and then expect to retake the quiz when you figure out what's wrong. Here's the thing. I think the quiz is 8 or 10 questions long, and they're scrambled. So the questions are scrambled and the answers are scrambled. You have to actually work the problems. It's not going to be something that you can say, oh, well, I got one last time wrong, so this time it's going to be B. Because the same answer, you might not get the same question, and even if you did, you might not get the same answers in the same places. So don't go over and just shotgun it. Don't just go throw answers at it. Sit down and think about what's going on. If you have any issues, email your teacher. Those links will be on Blackboard to help you know the email addresses if you still need them. All of this is due by 4 p.m. on Sunday. You have to complete the quiz by 4 p.m. on Sunday. This will not get reopened. You've had lots of warning. Please do not procrastinate. Start this early and get it over with, just so you can enjoy the rest of the weekend. Like I said, if you have any questions, give us an email, and we will be right on top of that to help you out. Thanks so much. Bye-bye.